Welcome to Lecture 9, which is entitled Double Integrals over Rectangular Regions. So we are now moving into the next portion of this course, which deals with integration. And so this is the first lecture on integration for the multivariable case. So the material for this lecture comes from section 16.1 of the textbook. And the objectives are to develop tools for computing double integrals in a Cartesian coordinate system with constant integration limits. And the concepts and visualization skills that you'll acquire are what we mean by a Riemann sum in 2D. I mean, all problems in integration basically evolve from a sum and in the limit become an integral. Secondly, relationship between integration limits and straight lines bounding the 2D region. And then the other thing is changing the order of integration. The fact that we are integrating in two directions means that we have a choice in terms of the order. Do we integrate with respect to x followed by y, or the other way around? This is called an iterated integral, and it doesn't matter which way you do it, but there are some caveats in terms of how you should basically do things from a procedural point of view. All right, as usual, this is just a summary slide indicating the different slides in this presentation, so I'll just skip over it. All right, so to begin with, I just want to give a general overview of multivariable integration. And so I've basically organized this slide in terms of three different columns: single variable, two variable, and three variable. So let's quickly review the single variable case. If I give you an integral between upper and lower limit b and a of f of x dx, then dx represents a differential length, but f of x cannot take on different meanings. So I've given you three specific cases that one could consider. One is that we let f of x equals 1, but we give it no units, in which case we're just integrating from a to b dx, which is just the length of the line. And the units of that would be meters. I mean, dx is units of length, so it's going to be meters. Second option is f of x is some function, right? And its units would be a number sign divided by meters, where this number sign would be some physical quantity such as kilograms. So for instance, if we're interested in calculating the total mass of a straight line, where the mass is not distributed uniformly, then it would be a mass density, kilograms per meter. If you integrate, the result would be the total mass, the number represented in this case, a number sign representing kilograms. And the third option is if f of x is greater than 0 and has units of meters, then basically what you're computing is the area between a curve defined by f of x and the x-axis, between x equals b and x equals a, and the units in this case be meters squared, which is in fact an area. For the two variable case, then we're going to define dA as a region, a differential area element, and so you're integrating over a region. And similarly here, we have basically f of x of y now. It's two variables, can take on different meanings. The first one where we let f of xy equals 1, but don't give it any units. In this case, basically, you're doing a double integral over dA, which is nothing more than integrating the area of the region, and the units would be meters squared if we're talking SI units. Second option is f of xy is some function, right? And its units would have something number sign divided by meters squared, right? Number in this case could represent kilograms. And so this would be a mass density in units of kilograms per meter squared. So if I integrate this kilograms per meter squared over the region of interest, I'm computing the total mass of that particular region. And lastly, if f of xy is greater than 0 and takes on the units of meters, then what we're computing is the volume between a surface, right, some arbitrary surface of fxy, and the z equals 0 plane. And so this would be units of meters cubed, so effectively it's the volume. Lastly is the three variable case, and of course one can go on, 4 and 5, but these are the ones of practical significance to most of us in the, at least in the undergraduate curriculum. In this case, it's a triple integral. D represents domain, which is a volume, and dV is the differential volume element. So again, we have three cases to consider. One would be if fxyz equals 1 and has no units. In this case, we're integrating the volume of the domain, and the units will be cubic meters, meters cubed. If fxy is some function, okay, its units would be number sign divided meters cubed. So for instance, number sign, this could be again kilograms. It could also be charge. So this would be the mass density. In this case, though, because it's of a volume, it's kilograms per cubic meter. And if we integrate that mass density over the volume, we're computing the total kilograms within that volume or domain. And lastly, if fxyz is greater than or equal to 0 and units take on meters, then the units of fxyz dv would be meters to the power of the fourth. This is a fourth dimensional volume between a 3D volume and w equals 0, which would be a hyperplane. Right? Of course, this can't be drawn and doesn't have any real physical significance, but I've put it here just as an illustration that you can keep on going to 4 and 5 variables and so on. So this is more or less a summary of the way in which these integrals can be utilized. All right, so now we basically look at the whole process of integration, and we start by looking at a function on the left, and we're trying to approximate it by a series of rectangular columns. And these rectangular columns basically will have a certain area and a certain mean height. And what you're trying to do is to best fit the height to do a sort of an average of a height over that particular region. So this is what you're trying to do, is approximate the function by rectangular columns. All right, if we look at this in more detail, you look at the curve, which is z equals fxy. And let's say this is an example where z equals fxy basically is units of meters, height. And the region, of course, units of meters squared. So we'd be computing the volume between the z equals 0 plane and the curve z equals fxy. The region would be the xy plane. And what we do is we discretize the region into a number of squares. And what we do is we pick the center of each square as a mean value of coordinates of xk star and yk star. Right? The area of each one of those little rectangles, right, will be just delta xk times delta yk. Typically, the areas would be identical. In other words, the delta xk's and delta yk's for each one of those little squares that you see here are more or less the same. They don't have to be, but they're typically taken to be about the same. All right, so this is basically how you discretize the region. The next step basically is to add one additional element, and that is the height at a particular location. So if we look at a particular location, right, we choose a height which is a mean value of the height at the black point that you see here. So for instance, you've got a portion of this top of a rectangle that extends past the surface and goes behind the surface. So on average, this is a good representation in terms of an average of this region in terms of the vertical height. And you do this now for every separate region. All right, and then the question is discretization. In other words, how many little rectangular columns should you use? So you've got examples of 16, 64, 256. And you can clearly see as you introduce more and more little rectangular elements, right, each being smaller, that the approximation of the function gets better and better. And so effectively, if you really are interested in computing the volume, then this would be the sum of the contributions of the volumes of each one of those rectangular columns. And this is the basic expression that you see here. But of course, in the limit, since we're dealing with calculus, the number of columns will go to infinity, and the area of each column will go to 0. I mean, the product basically, the sum basically remains a finite number, but this is basically what we mean by calculus. And so this now becomes the definition of the volume. If the area goes to 0 and the number of elements goes to infinity, and you sum from k equals 1 to infinity of the area of a particular element and the height, the mean height, then this is by definition going to be the double integral over the region of interest of the function fxy dA. And then again, this is your differential area, and this is the differential volume. By the way, computers, for instance, instrumentation, digital cameras, they basically implement the Riemann sum. They don't do the actual calculus. They do a Riemann sum. And so, for instance, when you're looking at brightness control, what they do is they look at the average brightness, and then they decide whether or not they should be adding more light to an individual pixel so that the average brightness of the image as a whole is suitable. All right, so now we get to our first theorem, which is the Fubini's double integrals over rectangular regions. Certain conditions are, of course, imposed. We need to make sure f is continuous on the rectangular region. And again, because the rectangular regions means x will have some lower and upper limit, which is a constant. Similarly, c will have an upper and lower limit, which are constants. And the double integral of f over the region may be evaluated by either of two iterated integrals. We can either do integration with respect to x first between lower and upper limits a and b, followed by integral with respect to y between lower limits c and d, or we can reverse the order, in which case we do integration with respect to y first, which means from lower limit c to d, followed by integration with respect to x between lower limit a and upper limit b. And so now the next thing to do is to look at what is the interpretation of these symbols. These are symbols that were developed by Leibniz well back, I guess, in the 1700s or 1800s. It's a short form basically for integration, but they actually do have some physical meaning. So, in fact, this is the double integral that you'll see in the book. But be careful, because in effect, the moment we're dealing with a region, it's implied that it's a two-dimensional object. So, for instance, if we look here, this is the integral that you perform first with respect to c and d. That's y. So these are limits on y, c and d. But because it's a two-dimensional system, that means that x also should have a value. But since x is not mentioned, then you automatically can just say that x is an element of R and x is an element of R. So if x is an element of R, and c takes on a value of d here and a value of c here, what does that imply? That means basically we're talking about two lines that are parallel to the x-axis, one located at y equals d and one at y equals c. What about this? Again, here basically the limits would be the outer limit would be x here. In this case, the limits are x equals b and x equals a, but y can be anything. If y can be anything, then this represents a vertical line at x equals b, and this represents a vertical line at x equals a. So if you put all these lines together, what are you doing? You're creating a rectangular box, and everything contained within the box is by definition the domain of interest. So keep this in mind. This is shorthand, but this is actually the way you should read things. Okay, so this is just a summary then of what we just said here. So keep this in mind, even though the book doesn't necessarily use this type of symbology. All right, so now let's go through the actual integration process. And it's called the slicing method. You can either go in the x direction or the y direction. So let's look at each in turn and then just show the example on the left with respect to the slicing in the x direction. So this would be, say, the volume. This would have units of meters, dA. And so this is some arbitrary f function fxy dy dx. And so if we integrate, first we need to integrate this. This whole thing, when you integrate with respect to y, you basically are holding x fixed. X is treated as a constant. So after integrating, this will only be a function of x. That's why it's called a of x. So a of x would just basically, what are the units? Well, this will have units of meters. This will have units of meters, so this whole integral will have units of meters squared. So this represents an area. So this a of x would say, at this location, the area of this little piece that you see here takes on a certain value. Go to a new value of x, the area of this little segment is a different value, and so on all the way until you get to x equals b. If you integrate from a to b, what are you doing? You're sweeping this structure from to the back to the front, and basically you are mapping out the volume going between here and here. So this is basically called the slicing method in terms of how we look at things. You can also basically do everything in reverse order. I don't show the picture here, but you can do it for yourself. We'll do an example later where we illustrate that. In this case, we would have, first we'll do integration with respect to dx. So that means we integrate from a to b first. Again, this would have units of meters squared in area. But in this case, y is held constant, which means the final, final function, right, will be only a function of y because x will have been taken out. So this a of y basically would look like similar to this, except instead of going in this direction, it'd be going in this direction. Okay, so that's basically what we mean by the slicing method. It's an easy way to visualize it. Later on, you may not even use that terminology. You would just do the integral. It just becomes second nature. All right, so let's do an example using a slicing method in the x direction. We want to compute the volume of solid region bounded by the plane z equals 6 minus 2x minus y, which is this one, and the xy plane, which is this one down here, over the rectangular region R. 0x is less than 1, 0 is less than y equals less than equal 2. So it's basically in the first octant. So it's in this region here. So you have the limits of x equal 1 and the limits of y equals 2 here. So this is a picture that you'd be drawing. Okay, and you're interested in the volume in here. So if we're going to slice in the x direction, then we're computing basically the area for a given x. So in this, at x equals 0, you can see the area is quite large, but as you move out towards x equals 1, this area should get smaller. So let's substitute in for fxy here. We have 6 minus 2x minus y dy. Again, in this case, you're integrating with respect to y, so hold x constant. All right, so we just make the substitution, do the first integral. So if you integrate here with respect to y, this will be 6y, this will be 2xy term, and this will be y squared over 2. So that's what you see here. And then evaluate between upper and lower limit, and you end up with this, and this represents a of x. So you can clearly see at x equals 0, the area is larger. As x moves towards 1, the area gets smaller. That's in agreement with the picture that you see here. So now we integrate this, and we'll get a value of 8. I haven't put units here because the problem doesn't specify units, but if this were basic SI, this would be 8 cubic meters. That's the volume. All right, now let's do it in the y direction. So if we're doing it in the y direction, we just reverse the order of integrations, and again, an iterated integral. So in this case, we do integration with respect to dx first. Still the same function, but if we integrate this now with respect to dx, the resultant will be just an area with respect to y. So we're looking at basically different segments as we move in this direction. Here's just one of them being shown at some specific value between y equals 0 and y equals 2. Looks like it's more or less at y equals 1 here. All right, so we integrate now with respect to x between 0. We take integrate the ay, we end up with this, simplify, and so this becomes the area with respect to y. Clearly at y equals 0, it's larger. At y equals 2, it's a much smaller area. Now integrate this, and again, we'll get the value of 8. So the answer is exactly the same, which it should be. Again, if it's SI units, it would be 8 cubic meters. So the question in this case would be, does it matter which way you do it? No. In this case, because the limits are numbers, I mean, it makes no difference whether you do it one way or the other. But once we start dealing with regions which are not simple, then the order can make a difference in terms of either it's a simple integral or it's a difficult integral. And sometimes it'll be easier to work with one form versus the other. Okay, so the last slide basically is what do we mean by an average? So for example, in one dimension, if we compute an average, it basically means this. F bar just is average. You take the function of interest, you integrate it between the lower limit and the upper limit, and you divide by the difference. That's the length going from a to b. Okay, and b minus a would just be the integral of ba dx. If we now extend this to 2 dimensions, then what we're working with here is an integral over an area divided by an area. Well, the area of the region will just be double integral dA. So here we would have to substitute the function and integrate. Here we just integrate dA, which would be the area of the region. So let's take an example for the 2D case. Find the average value of the quantity fxy equals 2 minus x minus y over the square, region being 0 is less than equal to x is less than equal to 2, and 0 is less than equal to y is less than equal to 2. And so more or less this is again in the first octant, which would be out here somewhere, and this is the region. So this, what you see here, is the stuff that you see shaded in blue. This gray is the actual physical plane. All right, so we need to compute the area, and we need to compute basically this term here. So let's do the area first. It will be the double integral dA. Again, this could be dx dy or dy dx. I've chosen dy dx. This integrated over the region, which means the limits on y, which are 0, 2, and the limits of x, which are 0, 2. If you do this integral, you'll get 4. On the other hand, for this integral here over the region, you have to substitute for fxy, which was a given. 2 minus x minus y dA. And again, how you choose dA, be it dx, dy, or dyx, doesn't matter in this case. In this case, we've chosen dx, dy. And so you integrate first with respect to x, holding y constant, between lower limit 0 and 2 for x. This basically is an intermediate step, and then finally you end up with this being a function of y, integrate with respect to dy from 0 to 2, and in this case the answer is 0. So the average value would be this integral, which we just computed, divided by the area of R, which we just computed over here, 4. In this case, the answer is 0. So this is what we mean by taking an average in 2D. That concludes Lecture 9. Thank you for listening.